Welcome back to Physics with Han. Today we're going to be looking at stationary waves. Stationary waves are different to progressive waves in the fact that the position of the crests and the troughs of stationary waves does not move. So these waves stay where they are. They don't actually transfer any energy from one place to another. Let's look at this animation. On the left-hand side of your screen, you can see a wave moving to the right. Now the wave is reflecting back to the left when it hits the fixed end, and this is the result. So a stationary wave is formed when one progressive wave moves to the right, then that progressive wave can be reflected back to the left, and these two waves will interfere. And I've frozen the picture here. This is a stationary wave formed from the interaction between the two progressive waves travelling in opposite directions. You can see that the amplitude of this stationary wave is really large, and you can see that there are points along this wave with zero amplitude, which are called nodes. There are certain conditions which are required in order to form a stationary wave, and you can be asked about what these conditions are. So the first one is that you need two progressive waves which are moving in opposite directions. You need these two waves to be travelling in opposite directions so that they can interfere. And remember, a stationary wave does not transfer energy from one place to another. So one wave travels to the right, it reflects, travels back to the left. The second condition is that these waves need to have the same frequency and amplitude. Here I've got one blue progressive wave drawn on the diagram moving to the right. Now I'm drawing the red wave, which is the reflected version of that progressive wave moving back to the left. Now, in this situation, these waves are going to undergo destructive interference. The peak of the blue wave meets the trough of the red wave and vice versa. And this results in a kind of cancelling out. And this results in the nodes of stationary waves. Now, if we look at a quarter of a cycle later, the blue wave has moved a little bit to the right, the red wave has moved a little bit more to the left. And what we get is these two waves which are actually overlapping. When this happens, we get constructive interference. This results in something called an antinode on the stationary wave, which is where we get an amplitude which is much bigger than that of the individual progressive waves. A stationary wave can only be formed at something called a resonant frequency. And a stationary wave will have different resonant frequencies. Here, what you've just seen is me trying to find the exact time that it's taken for this complete wave cycle to reach the end. And you can see that it's 1.2 seconds on the little blue timer. So, in order for me to find the smallest frequency, which is called the first harmonic, that this stationary wave will oscillate at, I can times that number by 2, because I only want 1/2 of the wavelength to be present here. So 1.2 times 2 would be 2.4. That is the time period for half of the wave cycle to pass. Then to find the frequency, you do 1 divided by that. So 1 divided by 2.4 is 0.42 hertz. So I'm just decreasing the frequency to get to 0.42. Okay, so at this frequency, you can see what happens. So the first progressive wave is coming in from the left. It's going to get reflected. This is in slow motion. And in a minute, you'll see what we get, speeding it up. Okay, so you can see that half of the wavelength has fit in along the length of this string. There are 2 nodes at the end and 1 big antinode in the middle. This is the smallest frequency. called the fundamental frequency or the first harmonic. So the first harmonic is going to be at the lowest frequency that the wave will be oscillating. On the left-hand side, I've drawn a fixed end, and then on the right-hand side here, that little black box, that is going to be my oscillator, the thing that is driving the wave. So you get these loops formed. Here you can see there's just one loop. The wave moves up and down, and it will keep oscillating up and down. If we call L the length of this string, we can see that the length of the string is half the wavelength. Moving on to the second harmonic then, here you can see we have two loops. If we count the nodes, we've got 3 nodes, one at either end, one in the middle, and 2 antinodes. Here we can see that the length of the string is equal to a full wavelength. And I'm just labeling on the nodes. Like so, 3 nodes and 2 antinodes for the second harmonic, which is at a higher frequency than the first harmonic. The third harmonic then, again, drawing my wave on and then drawing the dotted line, which is showing how the wave is actually moving, oscillating backwards and forwards. This stationary wave formed is at a higher frequency than the second harmonic. You can see here that the length of the string is actually 1.5 wavelengths. You can see that 1.5 wavelengths fit onto this diagram. In terms of nodes, we've got 4 nodes, and you can see that we have got 3 antinodes. Let's look at an exam question. We've got a standing wave set up on a wire of length 59 centimetres. It's vibrating at 150 hertz. We need to find the speed of the waves. So I'm just writing down information that we've been given. Length is 59 centimetres. Now, this is the third harmonic. So the length is equal to 1.5 wavelengths. So we can use the fact that the length of the string is 59 centimetres to help us to find the wavelength, just by rearranging that equation that I've written down. So 59 equals 1.5 wavelengths. So if you rearrange that, the wavelength is going to equal to 59 divided by 1.5. Putting those numbers into your calculator, you get 39.3 centimetres. Remember, this is in centimetres because I put the 59 in before in centimetres. If you want to, you can convert to metres straight away. Now, we need the speed of the transverse waves. This equation should be on your data sheet. Wave speed is frequency times wavelength. Here we're given the frequency 150 hertz. The wavelength we just found, again, you might want to convert to meters here before putting the number in. That is going to give you 5,900 centimeters per second. If the question doesn't ask you for the answer in meters per second, you could just leave it like that. Or you could convert and you would actually get 59 meters per second in SI units. A second example, this wave is vibrated at a frequency of 300 hertz. So this is still part of the same question that we just did. The frequency for the third harmonic in the last question was 150 hertz. So you can see that to get from 150 to 300, we've had to double the frequency. So that will help us identify what harmonic we're currently at. And that is the 6th harmonic. So using that information, we can sketch onto this diagram what it's going to look like. I've mapped out the nodes before I try and draw the wave on, just because it makes it a little bit easier. but yeah, mine isn't perfectly symmetrical. So you can see here that there are 1, 2, 3, 4, 5, 6 loops for the 6th harmonic. The next stage is that we need to mark on 3 points A, B and C that oscillate in phase. So that means they're at the same point in their cycle as each other. So here I've marked on A, B and C.